I'll be discussing the work we are doing over Karnataka, basically the modeling studies. So the modeling, what are the modeling efforts we carry out in our institute in simulating the extreme rainfall events over Karnataka. And as an outcome of the extreme rainfall events, mostly like we realize through floods. So I will show few slides where like we have put some effort in simulating the floods also over Karnataka. So and I will also show a few results where like how data simulation, so which is the theme of this conference. So how data simulation can improve this forecast. So coming to the extreme rainfall event, so why it is so important? So because something which is very critical for the country, for the state, like researchers, like there will be always a pressure on the researchers to come with more ideas, come with more solutions from the government side. So why it is very important for our country? Because if you see in this chart, you can see that we come in the red spot, hot spot. So like we get, suppose if you classify the countries in terms of the weather hazards. So we come in a hotspot region. So we receive, if you compare we come in the top category. So coming to the how now, so we know that we are prone to the hazards. So now come to how we to tackle it. So one important aspect when come to the hazard management is like giving a forecast in time. So so we have events like meteorological or weather hazards of different time scale. For example, monsoon is seasonal. So these cyclones come in a week time, and thunderstorms happens for a few hours, like that, right? So if you see in this graph, so you have the see when the time scale changes, so your challenges also keep on like increasing. If you see that the x-axis, you can see the different application. See, like for example, like now you want to protect the life and the infrastructure damage due to a flood. So it happens over a period of like half an hour, 1 hour kind of thing. So when an intense rainfall happens, a flash flood happens, and it happens in a few hours of time. So the forecast need to be like for the like next few hours. So like for different applications, the duration of the forecast is different. So when it goes, the forecast goes from a shorter period in terms of minutes to years. So as the forecast duration grows, like the length grows, so you can see the uncertainty keep on like increasing, because our system is dynamic and most of these models need initial, like though we start with an initial condition, after a period of time the model is driven by the boundary condition, mostly like influenced by the boundary condition we provide. And see, like for a country like India, many recent studies, not only one study, many studies report that though suppose you say all India rainfall and all, doesn't show any much significant trends, but still when it comes to extreme, the number of extreme rainfalls are increasing. Though the total or average rainfall is constant or like doesn't show a significant strength, the trend in the extreme rainfall, if you take different region, it shows a significant increasing trend. That means the duration, like the rainfall duration is decreasing, but the high intensity rainfall events are increasing. So that compensates the total rainfall. But so that is more challenging or riskier. Like see, when it comes to early days, you may be like monsoon season and you may be like seeing continuous rainfall of like small intensity. But nowadays it happens like that the duration of the rainfall is not so long, but it happens the same amount of rainfall which we used to get in a 3 or 4 days period, we are getting in few hours. So that is happening in many parts of the country. So it is a challenge, we need to tackle it. So ERC, once the extreme rainfall happens, when it comes to the humanity, the major problem or like major hazard or in terms of it is like that, the death happens due to the flash flood. And if you see this data, we can see that we comes like along with China, we comes in the topmost category of number of flood events. And the more interesting thing is that in our case, the number of death is higher than the number of flash flood events. If you see, I think most of the other countries, if you see that the death due to the flash flood is lesser than the number of events. In China, if you say it is only 50%. So if you say the number of floods and the number of death, but in our case, even it is higher than the flood events. So if in the country, if you see the state-wise, see we can see that like states like Bihar, Kerala. Actually, Kerala may be coming in the top category maybe because of the notorious 2018 floods. So these states like many times we witness flash floods and many loss of lives we are like witnessing in recent past. So now coming to the Karnataka, so considering all these things, we have like over the past 10 years, we are putting sincere like many efforts to simulate the extreme events in Karnataka region. So what we basically does is that we like Karnataka State Disaster Monitoring Center have a very good network of observations. So they have around like, it was little old figure. Right now they have around 8,000 plus rain gauge observations and they have around 1,000 plus TWS observations distributed across the Karnataka. This data is available every 15 minutes, like as part of an MOU, like we have the access to this data set. And like regularly, like we used to like see the impact of this data set in the model simulations we carried out. And coming to the model performance, when we use this kind of a model for a prediction purpose, the model errors basically like can come from the like an intrinsic behavior of the model. Like one is like it can come from the data. Suppose how accurate or good data you provide as input, like your accuracy or the simulation accuracy will be proportional to the input data. Then another source of error is model physics. So you may have like all of those who may be working in the modeling, so they may be knowing many parameterization scheme and all those things. So that how good you parameterize like whether radiation, whether it is rainfall, whether it is like land surface flux or lower boundary surface. So how good you parameterize the physics, so the model accuracy depends on that. Then comes like from the numerics, like because we'll be doing a lot of like because atmospheric like flow is a continuous flow. So a continuous problem we are discretizing and we are solving it. So we will be like we are solving it numerically. So because of the numerical solution have its own limitations, so the numerical errors can come and like when we do when we formulate the model, we do a lot of approximation in the basic equations which govern the atmospheric flow. So those approximation also can cause like minor errors, and over the period of time that error can multiply and can grow over the time. And which kind of model grid you are using, whether it is Rekha, C or B, whatever kind of model grid you are using, that also like can contribute to the model error. So basically this error can be classified into systematic and non-systematic. Systematic is something like that the errors which have a pattern, like suppose a rainfall model predicts rainfall over a region, daily rainfall or seasonal or whatever rainfall. So if you see that there is a consistent overestimation or underestimation, so that is kind of a systematic error. So if we put a like bias correction algorithm, we can easily correct this kind of error. But there is another set of error which is like random, like it doesn't follow a pattern or behavior or like some kind of a nature. So in that case, very tricky, and mostly like this is addressed to data simulation. So this is the forecast system we used at our institute. Like, so we are now for last more than like 10-15 years we are working in this forecast system. So basically, like for like earlier we used to give the forecast operationally. In the recent past, mostly we does in the research mode. So we used to assimilate satellite data and the real-time case NDMC data and the data which is publicly available from the IMD website. And we earlier used to have some observation towers, those data also we used to put. Then the radio sonda data which is publicly available, that also we used to assimilate. So this data set goes as kind of a quality control. Then the quality control data will go to the data assimilation system, and then it merge with the using the first guess, it make an optimal analysis, and then it gives the initial condition to the model, and then we make a forecast, and then the forecast is customized for different applications. So this is the forecast domain we use at our institute for particularly. Actually, most of our work are focused over Karnataka, because earlier when we started the project, mostly it is funded by the state government. So most of our work we are focused over Karnataka. So this is the domain configuration we use. It like something like outer domain is 27 kilometer and the second domain is 9 kilometer, which covers the Indian region, and the innermost domain which covers the Karnataka. So that is a 3 kilometer resolution, and we use one more nesting for the forecast over Bangalore's urban city. So there we go something like sub-kilometer level. Like we did some work, so around 600 meter resolution we have run the model. So now coming to the extreme rainfall event simulation. So we need to so before we use any model for operational purpose, we need to really calibrate or test the accuracy or skill of the model. So for evaluating the skill of the model for extreme rainfall events, the challenge is finding the extreme, because extreme definition is subjective in the sense that the threshold which define extreme for a particular state or a particular region may vary from a different region because of the climatology, rainfall climatology of that region. Because for example, Karnataka, if we say about Karnataka, the extreme threshold value for the rainfall over coastal Karnataka or Malnad region, and when it compares to North Indian Karnataka or South Indian Karnataka, this varies. Because coastal Karnataka, we know that, and Malnad region we get very high intense rainfall. But when it comes to South Indian Karnataka, we get relatively less rainfall. And we have a North Indian Karnataka, the rainfall is much lower compared to these other two regions. So what we did is that we, for a 5 to 6 year period, so what we did is that we have done a frequency distribution of the rainfall event based on their intensity. So from the distribution, so we have identified the events which are rare events, in the sense that from the distribution, so from the distribution tail, you take a 99.993%. So whatever the events comes there the rest in the tail portion of the distribution, so that we consider as high intensity extreme rainfall. For see why we did year wise, because there is a possibility that suppose we don't do analysis year wise, because many times it happens that some particular year have lot of flood events and many other events. So for getting a spatio-temporal distribution, uniform spatio-temporal distribution, we have done the analysis year wise. So based on that, we have, for example, the threshold, the figure which I show is for coastal Karnataka. So here we can see that for each year also the rainfall threshold varies, but on a somewhat similar range, but all the threshold is about 250 millimeter, that means 26-25 above centimeters. And so year wise we have find the extreme rainfall events. These are the, basically 2015 we have 3 events comes under that category, above that percentile. 3 events are shortlisted in 2015 above that threshold, and 2016 4 number like that. So then with the same exercise we did for South India Karnataka. So there, like you can see that the threshold is lower compared to the coastal Karnataka. So because even some year like it was like 152 and some year it is, so that itself shows that year wise also it shows a tremendous variability. Then the same exercise we repeated for North Indian Karnataka. So there also, like you can see that lowest compared to other two regions, the threshold is much lower in these regions. So but the threshold is lower, but we have a lot of high intensity events. Number wise, there are a lot of extremes in those, like in the North Indian Karnataka region. So from these events, year wise we have selected year wise we have selected 5 events per year we have selected. So totally we have selected around 45 events we have shortlisted. Then we have, from using our model configuration, we have seen how the model performed in simulating these 45 ERE cases. So we have done a overall individual event wise analysis, as well as we have done a statistical validation based on the 45 rainfall events we have selected. So what we did, initially what we did is that, because some of our earlier one experiment we found that the model skill, rainfall skill is very much sensitive to the initial cover, like at what time you initialize the model. So we did an experiment by simulating these events at 2 different initial conditions. So like the average rainfall based on these 2 different initial conditions in comparison to the observation clearly indicates that the simulation which initiated at 12 UTC yielding relatively better forecast compared to the forecast which initiated 0 UTC. And so we did a statistical analysis of computing the bias and RMSE based on these 45 events. So here also it is clear that the bias and it is much lesser in 12 UTC forecast compared to 0 UTC forecast. So now after configuring the model and finding what is the realizable skill of the model, so we have assimilated the available observations over Karnataka to see how data assimilation can improve the forecast. So initially we used the 3D VAR data assimilation scheme for analyzing. So I'm not describing this, but because maybe for last 1 week you may be hearing this only. So the data assimilation, so it's a process where you have the observation, you have a first guess that is from a different model simulation. So you merge these 2 data set to make an optimal analysis. So in this process, you may be comparing the values. Some of the observation we may be rejecting. Some of the observation we may be doing some kind of adjustment. We will be giving some weightage to the observation. We will be giving some weightage to the first guess. And not like that we are simply giving 100% weightage to the observation or 0 weightage to the first guess. So many times it is kind of a way, we give weightage and we make an analysis based on the weight. So this is the process. So you have the observation undergoes kind of quality control and pre-processing. Then you have the first guess. So the first guess you merge with the observation, then you run a 3D VAR, then that 3D VAR output you give for the model forecast. So this is the typical 3D VAR simulation. Here you have a cost function, you minimize the conversion to find the value of optimal value of X. So this, anyway, of course, you may have listened to many speakers and you may be knowing this. So the data set we used for our experiments are we have used the AS data set. So you may be familiar. So AS is temperature and humidity profiles and dew point temperature profiles. And the wind observations we have taken from the SCAT, wind speed and wind direction. And we have the available buoy observations over the ocean from the Rama and Mood buoys we have collected. and the data set KSNMC network observation data set which I showed earlier. So we have temperature, humidity, and wind speed, all the basic, and even pressure from this KSNMC network. So that also, those are in situ observations that also assimilated. And the MODIS observation, because why we used AS and MODIS, because many times, suppose you say an event, you may not get a, because you may not get a proper pass from the AS or MODIS, like, so that's why we have used both AS and MODIS, so that we get a better coverage for our when we do the simulation for a particular event. So MODIS profiles also we have assimilated. Then the available radio sound observations. Then like SSMI derived wind speed and precipitable water also assimilated. And the windsat observation like wind speed, direction, and precipitable water is also assimilated. So this is the assimilation like cycle we have followed. So we started our assimilation something like 15 hours before. So every like 3 hours we have assimilated the observation. Then from 0 we have given a free forecast. And these are the like for a particular, just for one example, for one event, these are the set of like observations available for simulation. So the KSND network observation. Then you have the synoptic observations like TWS observation 17. Then you have a radio sound observation of that particular day, because it varies. If you have used the radio sound data, you may be knowing that it varies from day to day, because it may not be a constant number of radio sound available for all the days. So like that day it was like 96 radio sound, and buoy data available was around 19. And the AS and MODIS profile, we have a quite number of profiles, and the wind observation and the SSME also a good number of observations we have assimilated. So, so this is like that we have done an experiment where like we compared that how like, see, you do a 3D VAR at a single time and you do a 3D cyclic 3D VAR. So we did conduct a different experiment, but like this is like 3D VAR at a single time, and this is the corresponding control experiment where we didn't do any assimilation, and this is the control experiment where we done a like a cyclic forecast, then we did a free forecast but without any assimilation. Then we have done a 3D VAR assimilation where we have done a cyclic assimilation around 3 hours. Then from the 0 UTC we have given a free forecast. So the results show that like if you see that the rainfall pattern, if you see the observation, we can see that the rainfall is more focused on the Western Ghat region, and there are many pockets where rainfall is not available. But the cyclic CDVAR compared to the other experiments, the many region where that it was wrongly showing the rainfall in the control experiment and even 3D VAR at single time. So that those rainfalls, that overestimation is reduced in cyclic 3D VAR. We have done one more experiment. There what we did is that, see, because there are like many times when we do this kind of work, you may also received. Many times you may get comments from the reviewer, like, because mostly we use the NSUB or like GFS first guess. So a comment comes like that, okay, like in the GFS, most of these satellite observation, many observations are already going in the GFS as part of the global data assimilation system. So we did an experiment to see that how this our assimilation of data set compare with the GTS global data assimilation network, which is going in real time to the operational forecast models. So for a particular day, like August 14, there was a flood, like extreme rainfall events for particular Bengaluru and all. So that particular day, one experiment we have conducted. So this is a control experiment where we didn't do any assimilation, and this is the experiment where we have assimilated the satellite data we derived as well as the in situ observation from the Karnataka state. And this is the default like before like GTS observation which goes routinely to the data assimilation system. But it shows very clearly that there is an extra merit of the data, in situ data we assimilate. So the many portions it was showing rainfall in the assimilation with the GTS data, it is reduced in the assimilation with our in high density in situ data set. And so then what we did is that we have compared to see that actually I have shown the list of different observations available. So we have satellite in situ data, satellite wind, satellite profile. So to see that which data set makes higher impact or like which data set have a predominant impact on the forecast. So we did many sensitivity experiments by combining various different set of observation. So you have a control experiment, no assimilation. Then you have a experiment where we have assimilated only ocean winds. Then we have an experiment where we assimilated the profile. Then we have an experiment where we assimilated the station data. And we have an experiment where we assimilated all the observations. So like here also we can see that ocean winds, if you see that compared to the ocean winds and the station data, if you see these patches and all. So like many places the station data like relatively improved the forecast compared to other data sets. So this is the statistics we computed. So we have computed the improvement, like you see, for example, how much the RMSC root mean square error is reduced with respect to the control experiment. So here the CND means that control experiment where we didn't do any assimilation. Then you have an assimilation experiment. So this index, like the parameter shows how much the assimilation experiment reduced the RMS error, RMSE with respect to the control experiment. So here the positive area in this, like for example, like blue area represents the improvement with respect to the control experiment, and the red area shows that the assimilation experiment even performed worse compared to the control experiment. So like if you see that you have the more blue area compared to the red area, so it shows that assimilation have merit over control experiment. So like when we validate the rainfall, so it is like very usual practice. We compute the various skill scores, like threat score. You may be knowing that threat score, equitable threat score, and all these scores. So we have also computed those skill score to evaluate our forecast. So we have computed the improvement parameter based on the threat score. So here also we can see that the blue area shows that the more blue area compared to the red or like the negative area shows that the skill score, model skill is improved after the assimilation. So this is the like different category wise how these different data set assimilation performed. So here also we can see that when it comes to high intensity rainfall and all, satellite profile make a like the score is very high for satellite profile, but for the lower threshold the impact is similar. So this, like in addition to the rainfall, we have checked how the model, like other meteorological parameter like wind speed, humidity and all after the assimilation, after the forecast with the control and assimilation, how the forecast whether it is improved or degraded. So here again, like blue area is improvement with respect to the control. So we can see that particularly like of course like after the wind assimilation, the wind speed, the forecast except the Western Ghats, it is significantly improved. But when it comes to humidity, particularly the northern part of Karnataka, for whatever reason, the assimilation like doesn't improve the humidity prediction when compared to the control. So we also studied the seasonality because we conducted the experiments throughout the year. So we conducted like experiments like taking the cases during the southwest monsoon and northeast monsoon. So there we found that the impact, forecast impact is relative assimilation. After the assimilation, the impact is more during the northeast monsoon when compared to the southwest monsoon, because one reason for this is like that we are assimilating more local data. So the events during the northeast monsoon, the nature of the rainfall is more localized, and here it is more governed by the large scale phenomena, large scale circulation. So that may be the reason we are getting more higher impact in northeast monsoon season compared to the season. So this is an experiment we did for the Bengaluru urban region, how the model performs. So so we have a control experiment, and then we have a an experiment where we assimilated the data and the optimal model configuration. There, though like the location wise, if you see the peak intensity rainfall, it is shifted. When if you see the shifted, it varies from Hubli to Hubli, but in general, the best configured model is better than the control experiment in terms of predicting the intensity. And we have also examined the forecast skill for like localized and non-localized even, because I was showing the previous slide, the forecast impact or like the assimilation impact varies from localized rainfall and non-localized rainfall. So here we have evaluated the model skill for localized and non-localized rainfall. So interestingly, we can see that model skill is much higher, maybe like around 75% in non-localized, particularly during monsoon season and all. But when it comes to localized event of like non-seasonal localized rainfall, the skill is even below 50%. So we also like conducted a few experiments with the hybrid ensemble Kalman fetal and data assimilation. So here the difference is that in the 3D bar you use a static backgrounder matrix. So here we introduce an ensemble time which introduce a dynamic behavior to your background time. So so this experiment also conducted with the for similar data set, how the hybrid assimilation, hybrid 3D bar compare with respect to the traditional 3D bar. So here we have basically generated 90 member ensembles to to generate the backgrounder statistics. So here the assimilation data cycle is like we have started 24 hours before our so for free forecast period. So we did a data assimilation at 2 stages, at 24 hours before and at 12 hours before, and it basically it's a 1-day cyclic experiment we conducted. So if we compare the result, so the middle one is the rain gauge observed data, and the left one is 3D bar, and this is the hybrid experiment. So though like there is minor improvement when compared to like we are not seeing any drastic improvement, but still on large scale we have slight improvement in hybrid experiment compared to the traditional 3D bar. And the same is reflected, like we can see the bias in the 3D bar and hybrid experiment, and that more white area, which is the lowest bias region in hybrid experiment, shows that the bias is relatively low, lesser in hybrid experiment compared to 3D bar. So this is the for each hour what is the model bias for each forecast hour. Here also, except the initial few hours, the forecast error is much like is less, bias is less in 3D bar experiment, sorry, hybrid experiment compared to the 3D bar. So we also did some few experiments by assimilating the, see we have a group which is working on the GNSS GPS in our CMAX. So they have the ground-based GPS as well as the satellite GNSS based GPS data. So we also studied, conducted a few experiments to see the impact of this GNSS data set. So these are the GNSS data set which is available. So the first one is the radio quotation like GNSS data set, and with the ZTD, and these are the cosmic data set C2 cosmic data set also we have assimilated. And the fourth figure, this shows that the availability of observations from the RO, ZTD and cosmic data set. So this data sets also, like we have assimilated the same set of ERE events and experiments I conducted for 3D bar earlier I showed. For the same similar set of events, we have conducted the data assimilation of the GNSS and GPS profile, particularly like to study the impact of Karnataka. So these are the this is the way we designed our experiment. In all the data set, like in all the experiment, including the control, we have assimilated the prefer like that GTS data available for globally available for data assimilation. And then we conducted different experiment by assimilating GNS ground-based and radio occultation and cosmic data set. This is the result. So the first one is observation, and the second one is the control experiment where we didn't do any assimilation. The third one is like that we have assimilated all the GPS based observations. Here also we are not finding any like some dramatic or drastic experiment because this work we have started, but because there are many studies reported that this GPS GNSS data have many issues in the lower levels because of that boundary turbulence and all. So that actually now that we are calibrating that GNSS profile and we are planning to reconduct this experiment, maybe that is we need to see that whether that is the reason we are not getting much impact. But still, if we see that compared to the control experiment, like many portions, like we can see that it is slightly, if you see the percentage improvement, it is something like average improvement is 21% compared to the control. And it is the same for rainfall in terms of skill score, equitability score. So you have a 25% improvement compared to the control due to the GPS assimilation. And again, this is for surface temperature, but for surface temperature, we are getting much higher impact compared to the rainfall and other parameter. So this is for the profile. So profile also particularly except the lowermost level. So we are getting improved profile after the GPS and GNS data. Actually, this is the area. Actually, there are many studies reported. We need to really calibrate the GNS observation below 800 millibar. So that work we are doing that. So initially I was saying that, so when the year extreme rainfall happens, so when it comes to the practical application, so the outcome is like the humanity face it as a flood. So it affects our day-to-day life as flash floods. So as a modeler, it is important that once you predict the extreme rainfall intensity, how much the flood can cause, like how much the flood inundation it can cause or the cities or that in the urban region. So that is very critical when it comes to the management, particularly the state government disaster management and all. So what we did, as part of a project, we have developed a hydraulic flood modeling system. So what we did here is that, so we will run the WRF at very high resolution. Then the WRF model, we will provide input to the soil water analysis tool like SWAT model. So it's basically a hydrology model. So this we run around 40 to 50 meter resolution. Then the SWAT model is coupled with a HECRAS model. So the HECRAS, the advantage is that compared to SWAT, we cannot run it for very high resolution like in meters. So but HECRAS we can run for up to 5 meter. We can run the HECRAS model. The downscale data from the SWAT is the discharge data is given to the HECRAS. Then we have done the flood inundation for various regions. Some results I will show. So right now we have some few river basin. We have tested this model. We have tested it for Krishna Basin, Upper Jhelum in the Kashmir, and we have in the Uttarakhand Koshi watershed we have tested, and the Periyar Basin we have tested, and Kaveri Basin also we have tested. So this is the SWAT river discharge from the SWAT model for the longer period. So we can, this is for the Almora Uttarakhand Koshi watershed, and this is for the Kashmir region, and this is for the Kaveri. So we can see that it is the SWAT model is able to pick the temporal variability. Even if you see the seasonal as well as the intra-annual variability, it is able to pick the intra-annual variability. And the SWAT coupled with the HECRAS, we have used it for the simulation in the Kerala state, particularly that 2018 flood, and we tried some experiment in the Periyar and Pamba region. So these are the two rivers flooded during 2018 and caused a lot of flood in the Kerala region. So we have simulated the flood like height, flood inundation height in these two basins. The one is the first basin is Periyar and second is Pampa. So if we have cross-checked with the real-time flood maps, so the Hakaras model could capture that the highly flood area reasonably with good accuracy because we have checked with the real-time flood map panel. So we see here it shows that the Kuttanad and all based on this flood, this was the this are the simulated the flood water in this Kuttanad area. So it clearly shows that what are the regions where the flood inundation happened. So this shows that if you couple a weather forecast model with a hydrology model like flood model, so we can with a good reliable accuracy, we can generate flood inundation maps in advance and give to the disaster warning centers. So again, this is the temporal variation in the river in the discharge for the Periyar and Pamba basin. Actually, if you can see that this is caused actually the flood. You can see the 2018. If you see that on long time average, there is a very high spike. That's why even you can see that. Here also we can see that. I remember there was a one even here, and plus there is a 2018 also there was a spike in. That is why the flood happens in Kerala. So we used a swarm model for flood simulation in Karnataka. So here also we have coupled the swarm model with the WRF. So we have got the drainage map from BBMP. So Koramangala and Chalagata region. And Chalagata, you may be remembering the IT hub is in Bengaluru is witnessed a severe flood. So there is a Belandur lake which comes in this watershed. So we have for one flood experience we have simulated, and we could see that runoff and the nodes where the flooding happened. We could reasonably simulate how those the flood inundation, the runoff in each catchment area in this Chalagata watershed. So this work is still progressing. It is in the beginning stage. Thank you.
Okay, if there are no questions, let us thank Dr. Rakesh. Sorry.
Yes. Yeah, I didn't show that results. Actually, I have referred a paper. I showed a paper there, so we can get the detail in that paper, QJRMS paper. So what we did is that we have suppose we have over the Bangalore we have computer. So we have seen the spatial pattern of the rainfall. From that we have computed the number of pixels. So if the pixel if below 20% of the total area is witnessed a rainfall, we have considered as localized, and if it is above 50-60% of the total Bangalore area pixel wise, if it is rain, so in that case we consider as a non-localized rainfall. So you can get the details in this paper, QJRMS paper, how we have defined that, identified that, categorized localized and non-localized. Basically, we have used intensity plus distribution. So we made a combined index. Based on that, we have categorized localized versus non-localized. I couldn't get it. Yes. Yeah, see, here our focus was only over Bangalore region. So, yeah, I understood your question. So, what we did is that in the paper also it is there in the discussion part. We have we see when we set the domain, we have an outer domain which covers a larger region. So we have analyzed the large scale parameters in the broader domain. From that we examined and we could get inference that the system or the rainfall is caused by a localized trigger or convection, or as part of the rainfall was part of a large scale system or a localized system. Hmm. Hmm. Actually, see, I told now we have a GPS division there. So basically, they go and collect the observations also. So the DEM data, so whatever that's part of that, we have cross-checked the minute for computing the delay. We have used their help for cross-checking the DEM height. So those points where that they have field observations. So we have calibrated based on the data from our GPS team. Wherever possible, we corrected. Wherever possible, we corrected. Yeah, but that's what I was telling. There are issues. There are issues. Exactly, I was telling that, particularly in the lower level. So where particularly when it comes to mindfulness region and all, so there is an issue in the computing the delay. So that still we are working on it. We are having some issues.
So, yeah, if there are no other questions, let us thank Dr. Rakesh for this excellent lecture. Thank you. So the next speaker is Dr. Rekha of NESAC. So I'm happy to inform Dr. Rekha is a PhD from our department, IAST, and her supervisor is one of the organizers, Dr. Govindan Kutty. So Dr. Rekha is a scientist working in NESAC. She is working operational WRF. I think as part of her PhD, she worked on both variational as well as ensemble methods of data assimilation. I think I invite Dr. Rekha to give her presentation.
Thank you, sir. And I'm thankful to Chandrasekar sir and Govindan sir for giving me the opportunity to interact with you people, because here I'm not for any teaching or anything, just to share how we are doing the weather prediction for the northeastern region. Just now Rakesh sir has shown like 6,000 AWS network, and it's kind of joke for us, like in a region like northeastern region, we have near about 120 AWS stations, but still our forecasts are compared with forecasts of US. So you can think like how much we forecaster are like struggling. Everybody needs accurate forecast, but for accurate forecasting, what is required basically? And before going to that, I just want to give a brief introduction about the northeastern region. If you see the picture here, this is the northeastern region. And if you see, 2/3 of the region is almost covered by hilly terrain. So it's orographically very complex region. And if you see the dots here, these are earthquake. That means our northeastern region is almost sitting on a bed of earthquake. And then every year during the monsoon season, our region is affected by floods and eventually landslide. Then thunderstorm and lightning, every year's problem. And then avalanches in the Sikkim area is also a big problem, mostly during the winter season. And currently GLOF, that is the Glacier Lake Outburst flood, that turns out to be another emerging problem for the northeastern region. Last year in GLOF, one dam has fully washed away, many people died. So that is why I'm giving this background, like why we need to do the early warning, because eventually you people will also become forecasters, so you should understand the need of the region also. So, but unfortunately earthquake prediction is not possible, so as of now, so we are concentrating mostly flood for flood forecasting or alert generation, we need to forecast rainfall. then thunderstorm like lightning, and wherever possible weather related information we used to pass on. So if we talk about the disaster here, then we basically work for the preparedness part, that is the early warning. And seeing the vulnerability of this region, if you see this chart, almost all kind of disaster, like Northeastern region is a hub of almost all kind of disaster. So seeing that ISRO has set up a node at NSAC, the Northeastern Regional Node for Disaster Risk Reduction, and I am the coordinator of that region, of this division. And already NRSC is there, but seeing the vulnerability of the region, so that, because time is the very important thing during a disaster. So we at NESAC, we support all the state disaster management organization during the preparedness phase, during the mitigation phase, and even after disaster assessment using UAV data. So the main role of NERDRR is to create a single window platform, like whatever early warning, whatever we develop, we bring it to a common geospatial platform, and then the user, not only, for example, IMD is also generating weather forecast, and CMRW is also doing, then why we need to do? So we are not mostly duplicating the work. Whenever the user needs, we do the prediction, but we work with the parent organizations like IMD and all, and we take their forecast and we overlay the geospatial information like road network, settlement. Those informations are very crucial during the disaster time. So a like decision maker who is sitting in the DC office who doesn't know anything about geospatial technology also, he can or she can use the domain and can assess where the damage is more, where are the shortest route, how to set up the evacuation like camp, and also those informations we are providing using the platform. This is just the background of NERDRR, and now coming to how this started. Actually, we have got a project in 2009 from NIPCO, like whenever they release water, then it's a power grid company, so when organization, when they release the dam water, the downstream get affected and always create havoc, and in newspaper also there are lots of things come up. So they have approached us, they said like, can we predict the rainfall? So at that time, I just joined in 2009. And that time, our team was using some statistical method. And at that time, the prediction accuracy of the flood was almost just 20%. But with the involvement of the weather research forecast model into this structure, the improvement is, you see, now the average seasonal alert success is 85%. And this blue is showing that complete absolute success, and 20% is partial success in the sense like how the water level is increasing, but it's not flooded, but still the model is performing. And somewhere, always where there is a model miss or failure are always there. So that is how we have started the early warning at NESAC, because whenever we take up any work, we should understand the requirement. So from 2009, we have started the implementation of weather research forecast model for flood early warning system, thunderstorm nowcasting, lightning forecast, and rainfall forecast for hydroelectric power plants. And this is the kind of structure what we are using. Our resolution, we have started with 27:9 kilometer, then now to 3:1 kilometer. And thanks to Amit sir and team NRL for sharing their computational facility with us, because here I will not discuss much about the technology. Being a weather forecaster in the future, what kind of problem you may face, because you know all the technology involved, all methodology, all mathematics you know. But if we go for a operational forecast, you will face lots of issues. First of all, your computational facility. You should have a sufficient computational structure, infrastructure, so that you can run your model at a very high resolution. You cannot just merely use a 27 kilometer forecast for a region like Northeast. In Northeast, every half a kilometer, your environment, your atmosphere is changing. If you see in our office, if it is raining half a kilometer away, it is very bright sunny. So that kind of dynamics, you cannot, compare that forecast with 27 kilometer, never. So for that, you need a very high power computational facility. And then comes your data assimilation. Data assimilation, it's mainly depend on the observations. If you don't have observation, it's a kind of gigo. You are using very sophisticated data assimilation methodology. But if you don't have quality data, then you are getting garbage. So how to improve your forecast? So there are many things, and continuous validation is very important. So at ANISEC, we are using the weather research forecast model, and for operational, we are using 3D VAR. 4D VAR is also computationally very expensive, so operational we are not using. We are assimilating satellite data and GFS globally available data, what sir has already shown you. So BO data, radio sonde observation, CNOP observation, all those information we are assimilating. But AWS station, the problem is this data need to be quality checked. Some of the station in Northeast are such that every time you will see, it will show you 200 mm rainfall, which is not possible. So operationally, if you go, you need to have to see the quality of the data. So operationally, we are not using the AWS, we are using them only for the validation purpose. And if we come to the model structure, sir has already mentioned like we are getting error like numeric error, random error, parameterization scheme error, lots of errors are involved because it's just a model based on some mathematical equations, right? So what we can do for accuracy improvement, because weather research forecast model is not developed for India. We need to do improvement somewhere because not only data assimilation will help, okay? So first is our initial condition and boundary condition from where we are getting. How accurate those information for our domain. Then our model is consist of the dynamical module and the physical module. Dynamics improvement will be taken care of the assimilation. What about the physics? I'm happy that you have already attended Amit sir's presentation. They are developing a model for India with microphysical parameterization schemes. Because the WRF model, the parameterization schemes are not for India. So we need to do because if we can't develop the scheme, but at least we need to study the scheme, whether they're performing better or not for your reason. We cannot just blindly go and use some scheme used by some researcher in some publication, okay? So for any operational thing, you need to be very particular about the configuration of the model. So you need to see what are the microphysical parameterization scheme available, how it will perform for your domain, and then the best combination you will choose. If you see, these are some of the background study I'm showing. For India itself, many researchers have used different parameterization schemes and their performance, they mention differently. For example, here, your Canfritz and Better-Miller-Janzig is performing well. However, towards the southern tip, your Thomson scheme is performing better. That way you can see the schemes are performing differently. It's not like a particular combination you will use and it will work for your domain. So you have to be very particular about that while using the parameterization schemes available with any kind of weather research forecast model or any kind of weather model. When we have started, we have, this is our domain, this is the mother domain at 27 kilometer, and this is covering Northeast. And another problem that you will face while you choosing your domain is the CFL error. I think you have heard about the CFL error during this one, okay. So that error will blow up, or because WRF model become unstable, so that error will show, and that can be reduced either like selecting the domain judiciously or improving the spatial resolution or time step, because this is the northeastern region, very complex, and I have already shown it is covered by very hilly terrain. So if your domain will go over some steep mountain, then again this CFL error will come. So while selecting the domain, you will have to be very particular, and some R&D also need to be done while you select the domain. We have used some of the combinations that have been used for the Indian domain, and we tried which combination of, because why I am showing here microphysics and cumulus physics only, because we are dealing with mostly rainfall. And for rainfall, you are having one subgrid scale and one explicit rainfall prediction schemes. Your cumulus will give you subgrid scale effect of convection, and microphysics includes explicitly resolved water vapor, cloud and precipitation process in large scale. So if this schemes performs well, that means our rainfall prediction will be improved. So this kind of background sensitivity study you need to do, but unfortunately we don't have that kind of good computational facility at that time, so we cannot use, for example, if you see none of the combination is performing best. However, this Thomson and Gropal in the central part of Northeast, and then southern part, it is performing comparatively better in comparison to other combinations. And main thing is we are also comparing with the GPM data. And GPM data performance over the hilly terrain is also questionable. In many forums, they may ask, why are you comparing with GPM? We have our own IMD data, INSET data, all those things. But the thing is, like, we are mainly depending on GPM data, and GPM performance over hilly terrain is not that good. So that is why we need to compromise somewhere. Otherwise, for every like small nest we can make, and then we can use different parameterization schemes. But for us, because of constraint, computational constraint, operational purpose, we cannot do that. Then comes your static data. Like while we go for assimilation, before that, we need to configure the model. So the static data, we need to see the land use, land cover data, and the terrain information. The WRF by default data is 1992 old data, that is USGS, from USGS they are using. And however, if you see, there is drastic difference in the land use, land cover informations. So because while we are using the land use, land cover, it directly impacts the rainfall patterns. How the surface is interacting with the environment, there your land use, land cover plays a very important role. So you need to choose your land use, land cover data also correctly, so that the representation of the surface is correct. Okay, so we have used USGS data, and then we have used NRSC ISRO's land use, land cover data. And if you see, after using the ISRO latest data, like this is 2016 data, at that time we have 2016 or 17 maybe data we have used, and your correlation has been improved to 0.8. That means how much your land use, land cover information is impacting. It's not only about data assimilation or dynamic data assimilation, you need to be very careful about your static data also. So with good observation, good land use, land cover data, your rainfall prediction also improve. These are the AWS stations. This bar represents the AWS stations. If you see the USGS, how much they are deviated from the reality for both the stations. And if you see the biases, the most improvement is observed in bias and the false alarm ratio, although probability of detection and then ETS are almost similar, although NRSC is showing better result with NRSC LULC data. But there is improvement, major improvement in bias as well as false alarm ratio. So while configuring your model, you also need to be very careful about selecting your land use, land cover information. This is here the spatial representation. Those earlier one, what I have shown are comparing with AWS stations. This is a spatial resolution. Here you have see the biases observed here, like the overestimation observed here, how much it is improved with the land use, land cover data that we have we obtained from NRSC ISRO. USGS and ISRO are still a little bit comparable, but MODIS is too much of deviation, too much of biases are observed over the valley and even the hilly terrains also. So that is what I want to show, like what are the difficulties or what are the issues you may face and how you can improve before going to data assimilation. And then this is the terrain data. We have used terrain data from USGS as well as CartoDem. And this is an event when our model has drastically to underestimate the rainfall over the northeastern region. And then we have used the CartoDem. You have seen that underestimation have been improved. The biases have been improved here using the CartoDem. However, CartoDem, the results are not consistent sometimes. That's why for operational, we are still using the USGS. We need to look into the issues with the CartoDem data. We are not operationally using it because sometimes it performs well, sometimes some problem. So that is why we need to see where the problem is. Maybe while converting, there may be some issues because this data, CartoDem or whatever geospatial data, they don't come in the format that WRF can consume. So you need to convert the data in the intermediate format that your model can absorb the information. So in that process, maybe some issues happen or we need to compare both the CartoDem and USGS. That's why we are operationally, as of now, using only USGS data. Now comes to the topic of today's, why I have given the background, because you cannot just jump into data assimilation. Because before that, you need to see many other factors, and that is why I have given just a background, like you need to correct your static data also, then your physical representation of the model also, so that data assimilation impact is also visible. Because if your configured model itself is wrong, then whether you are giving good data assimilations, still your results may be biased. So Yeah, in ANISEC, currently we are using for operational 3D VAR, and however, we are planning to, move to ensemble-based forecast, because fortunately we will get a good HPC very soon. So, and I'm thankful enough that I have done my PhD under Kutty sir, Govindan Kutty sir, and he has given me a lot of exposure towards the ensemble methodology, because only deterministic models are not always like useful. For example, with the deterministic forecast, suppose you give this forecast ensemble mean, you have this forecast, but how you know that your forecast is correct? Do you have any statistical uncertainty information about your forecast? With what you will compare? Your errors are not improved. Whatever it is going, it is going. For example, today, while coming to this hall, I was kind of lost. I am the deterministic forecast, for example. So I am going outside. And I don't know, I'm moving that side because I don't have anything to compare my position. Amit sir has called me, no, this is your hall. So that is the uncertainty. Because all are sitting here, you all are ensemble members. So your statistics is compared with me, then my position has been shifted. So kind of ensemble is like that. So if you have the uncertainty information, then you can improve your ensemble members also. And finally your forecast. So that is why nowadays this is a trend, like we are doing mostly this ensemble thing, not we are depending on deterministic forecast. And this is the global forecast data that is globally available. We have sound data, synop data, then scattermetric data, SHIP. So these are all information that we have globally. Okay, and this is kind of supercomputer we need for running a very sophisticated data assimilation and model. So observations, if you have good quality, fortunately if you have good quality infrastructures, that lucky enough, you can do wonder. But we are not that lucky. We don't have that computational facility at that time. We have started with a 16-core machine, you can imagine. 16-core machine, that too for an operational forecast. And I cannot convince my boss, why you need a big system? Sab log kar rahe, everybody is doing, why not you? So it's very difficult to make understand the people who are not from this field, like we cannot do a standalone 2-core or 8-core machine for this. So we need to do lots of research, we need to show them result, and then finally, okay, chalo, we can get a small HPC of 120 core. So now we are having a system like 120 core, but we are lucky enough, we are getting access to NARL, as well as IIT Guwahati is also sharing their facility with us. And fortunately, we will get our own very soon. Then maybe we will also do wonder. And this is some of the results, like improvement, what you are observing. This is Guwahati region in Northeast. Guwahati is a city in Northeast, very famous city. There a very heavy rainfall event occurred, like within 1 hour, more than 100 mm rainfall occurred. But our model could not pick that event. Then we have do the postmortem where we are doing the mistakes. The thing is, like, we did not assimilate the AWS stations. And the in situ measurements are very, very effective, because if we talk about satellite data, INSAT 3D, for example, it is an IR satellite, infrared. And during monsoon season, our area is mostly cloud covered. So we are getting very less observations over our region. So our AWS station network should be improved if we want some prediction like this, accurate prediction, like more than 100 mm rainfall. If you see the dot here only, the more than 100 mm rainfall occurs. And with assimilation of AWS, that's what I want to show, like model has the capability, but what we will feed, it depends on that. It's kind of a child. We can mentor a child, we can feed whatever good, whatever bad. Depending on that, your model will develop. So it's also similar like that. And when we assimilate radar data into the model, if you see the rainfall, more than 100 mm rainfall prediction is picked up. So we are dependent on observations mostly. And when you talk about radar data assimilation, again the bottleneck comes how to convert the data, because radar data assimilation is not a big issue. Your model WRF already have all the like modules for assimilating the radar data, but your radar data comes in different format. For example, our Cherrapunji radar data, it took us 1 year to assimilate the data, because We don't have a manual how to convert the data. We need to do R&D, we need to do lots of effort. We need to talk to IMD, means we have the photos, but inside the data we are unable to use at that time. But fortunately we could decode the data, then this reflectivity and radial velocity we have retrieved from the data and we have assimilated in the model. And whether the data is really assimilated, that also you need to see. And you need to see if your observation minus background is improved. This is observation minus analysis for reflectivity and radial velocity, whether it is improved or not. Here we are assimilating only radar data, no other observations, to check whether our assimilation process is correct or not, whether we have really retrieved the data or not. So another thing is, like, while you assimilate radar data, one problem is if your background, like if your initial condition is dry, like your whatever initial condition from GFS or NCM or WF you are using, for example, this is the control, your environment is totally dry based on the initial condition. But when the model propagate to the, for example, to the next 6 or 12 hours, some local things are happening, because as I already told, Northeast is very dynamic in terms of atmospheric conditions. So within half an hour also some like devastating phenomena may happen. So those informations are not there in the initial conditions. And in that case, if you run the model with assimilation of global data also, your forecast will be kind of this, means it cannot pick up the local events. Then, but if in assimilating radar data, there are two possibilities. You can directly assimilate the radar data, or you can indirectly assimilate the radar data. Indirectly in the sense, from the radar data, you will retrieve the rainwater and water vapor derived water vapors, and then you assimilate into the model. So when your environment is very dry, if you just directly assimilate the reflectivity, sometimes you will get some clue, but sometimes it will be like the control run. Your convection will not be identified. But what we have observed, when we assimilate the rainwater and water vapor derived from the reflectivity, you see the mixing, the strength of the thunderstorm, it is improved. So that means your dry environment is adjusted using the information from the derived product, like rainwater and water vapor information. Because your reflectivity will only say whether precipitation will happen or not. It will not say anything about the temperature or humidity of that region. So if you retrieve, then even in the dry condition, if you assimilate the data, you are getting some promising results. And come to your satellite data. We have assimilated the INSAT 3D radiance data also. And this is the vertical profile. If you see, this is U component of winds, U and V, then temperature and humidity. If you see the profile, this is simple 3D bar with your global data, means pre-buffer data from GFS. This data is assimilated, and if you see the RMSE, and when you assimilate the INSAT 3D radiance data, your RMSE has been improved. Okay, so but the same is not observed for the humidity. We are always lacking in this, like humidity is not improved, but wind and temperature, it is improved. Radiances are mostly sensitive to the temperature, but it seems with the improvement with the temperature, it also triggered the improvement in the wind. With that, INSAT 3D radiance data assimilation have improved the wind as well as temperature. And this is just spatial representation. The radiance data over the northeastern region we have assimilated, and then we have seen that when we compared with the observed this AWS stations, this is a observed data, AWS station data from MOSDEC we have got. And then towards the western Assam or like Meghalaya region, this is the Meghalaya region, it is improving. Like this, like overestimation is improved with radiance data assimilation over the northeastern region when we compared with our AWS stations. That means radiance data assimilation has the capability to improve the rainfall forecast. Then comes your derived product like INSAT 3D atmospheric motion vectors. Like radiance data, they are direct product, so they have less errors. But your atmospheric motion vector or other whatever like geophysical term you derive from, then it has lots of assumptions and also the errors are more. So we have assimilated like AMV. This is like from GFS, this is global data. If you see how much dispersed the data, means like so much of gap. So we have assimilated inside 3D AMV, and that you see the uniformity of the data. Every grid, almost every grid is having some information. So that is what I want to show, like how your assimilation is important. Your local data assimilation is important. We cannot just depend on the global informations. And this is the wind, temperature, and humidity. And if you see the improvement parameters of 3D VAR with AMV data assimilation compared to 3D VAR without assimilation, if you see the improvement is 60% for wind, 64% for atmospheric motion vector. Relative humidity always less, but still it is improving by 53%. So that means your atmospheric motion vector is also showing better result over the monsoon prevailing region of India. Then comes your ensemble based forecast. We have used two methodologies, but basically currently we are using ensemble transform Kalman filter, and these are like member of the Kalman filter family only, ensemble Kalman filter family only. So we are using the Kalman filters for updating our ensemble members. So we are taking ensemble transform Kalman filter available in the WRF model itself, and then ensemble adjusted Kalman filter from the DART the module. So from there we are taking this filter for updating the ensemble members. And if you see the wind patterns during the monsoon prevailing season, although not much, but the strength or magnitude of the westerly wind is improved in the hybrid compared to the 3D VAR. And because of that, maybe the RMSE errors are more in 3D VAR compared to hybrid. And the improvement you are seeing towards the southern tip or in the Indian Ocean region, the improvements in the pink are showing where the impact is more with hybrid. Like your RMSE, if you see also the RMSE in the 3D VAR without any flow dependent error covariances is more in 3D VAR compared to hybrid. That means in hybrid, we are feeding the model with flow dependent information. In 3D VAR, we are using a climatological background error statistics, like last, for example, for this year if I am running, so last year what was the climatology of this region. So model will compare your forecast and observation with that. What happened? Okay, your model will compare your observation and forecast with the climatology. But it is not like that. Our atmosphere, our environment is chaotic, it changes every time. So our ensemble based forecast, it gives the flow dependent information, like every day what is the error in the flow, that information is included also. But why hybrid? Why not I'm writing ensemble? I just want to give a background, like I'm just writing hybrid. What is hybrid? Actually, hybrid is a combination of 3D VAR and ensemble, because while we take only ensembles, here we have taken 50-member ensemble, you can see. But we need to take like more than 50, like around 100 ensemble members. But same thing like computational facility, we cannot do with 100 ensemble members for an operational run. So what hybrid does, it takes the static like background error statistics also, and then from the 50 ensemble members, it also take the flow dependent informations. Then we can give weightage to the model, like the WRF model, how much weightage you want to give to 3D VAR, how much weightage you want to give to flow dependent error. That R&D also you need to do. Like for example, here we have given 25% weightage to 3D VAR and 75% to hybrid. So the model will take the error information that way. And then this hybrid becomes a combination where your statistical background error covariance matrix is supported by the ensemble based flow dependent errors, and that is why it is called hybrid. And this is for our northeastern region. If you see, my pointer is not working. Okay, so if you see the western part of Assam, this overestimation is drastically improved with hybrid. So that means flow dependent really have its capability. But don't look these red patches. Again, the problem is this is a very hilly terrain and we are comparing with GPM data. We need ground validations. So we are not banging our head over this region because we know our constraints. So that means over northeast also, our ensemble forecasts are showing better results. Then comes your INSET 3D atmospheric motion vector, because when we assimilate some observations, it also depends on the methodology what we are using, whether it is a static methodology like 3D VAR we are using or an ensemble. So that also we want to see. So sorry. So this is our model configurations, and we have made these experiments like where we use 3D VAR with assimilation of AMB, then hybrid with assimilation of atmospheric motion vector from INSET. And then if you see the earlier comparison where I have shown 3D VAR and hybrid only, here with hybrid, the atmospheric motion vector, when we have assimilated, the improvement is far better. Like the improvement is 77% for wind, then for temperature 70%, and for atmospheric motion vector. So that means it also depends on what kind of data assimilation technique you are using for assimilating your observations. So you need to do for like some R&D in selecting the observation methodology also, because it also has impact how your model will take the information. And this is like radar data assimilation. As I have told you earlier, when it is a synoptic kind of scenario, then your hybrid and 3D VAR almost showing similar kind of result. Not much of impact of radar have been observed. Even with flow dependent only towards the southern side of Assam, like this part, you will seeing some improvement. But radar data improvement is not visible, neither in 3D VAR nor in hybrid. But when it, and this is RQ, means this is the derived product, water vapor. But when it is an isolated system, isolated means like system just developed and dissipate within an hour or so. So this that kind of system when we have taken, and the initial condition doesn't have any information about the like convection or instability in the domain, then our 3D VAR and hybrid both shows the same clear no rainfall kind of scenario. But when we assimilate the radar data derived product, then you see kind of miracle, this no convection region has been replaced by a heavy rainfall event. There is shifting, although Rakesh has also mentioned, like we have so many issues, we need to tackle one by one. But you see, like with derived radar data assimilation, your improvement is more when you are predicting some isolated events. And this slide should be at the front. Why I keep it here, like slide quality is not good because I didn't get the original file. This I keep because I initially told that we need to see the initial conditions also. Three things we have seen, I mean, as of now we have seen two things like physical parameterization, then static data, and then assimilation. What about the initial condition? We are improving by data assimilation, but at least we should know the, like, what are the drawbacks, how they are performing over our region. So here I have taken three initial conditions from ERA, IMDA, and GFS. And for operational, we are using the GFS data only. And if you see, these are kind of some combination of parameterization schemes, 121, 161. So I'm not going into that. I just want to show by this slide that you need to be like, you should know how your initial condition is performing. And if you see, the GFS data is showing the maximum biases, whereas your ERA, because IMDA data also contain ERA information, so your IMDA or ERA is performing better for our domain. But GFS data that we are using for our operational forecast, because we can easily get the data downloadable, so we need to compromise many times. So that's why you need to check your initial condition also while you operationalize a model. And finally, after so many accuracies and all, our data goes to the hydrological model. But if flood happens, we get appreciation. It doesn't happen, we get banging. And that is like all weather forecaster in operational thing are facing the same. And then, okay, sometimes cyclone is also a problem for us, like this SIDR. If you see the red path, it is approaching towards northeast. Mizoram and Meghalaya and Tripura, sometimes it also face the problem due to cyclones. So we have done some research on that, how our ensembles like hybrid 50, hybrid 75, as I told, the weight is given to 3D VAR and hybrid is 50-50%, and weight is given to 3D VAR is 25, and then to ensemble is 75%. So if you see, the landfall position error have been very much improved with hybrid 75 compared to 3D VAR. and hybrid 50. However, not much improvement in the maximum wind error. Means intensity part we are still lagging behind, but positional error has been improved. That's why even IMD's forecast also for cyclone, if you see, very much accurate nowadays. And then we also do thunderstorm prediction, because northeastern region, as I said, it's a hub. You will get all kind of disaster. It's kind of disaster shopping center. So if you see, this is 2 thunderstorm events I am showing here. These white patches are showing dense cloud over the northeastern region. And this is the configuration of our domain. We have used 3 kilometers for the northeastern region for doing the simulations for the thunderstorm. And this is hybrid single. Okay, hybrid single means here we are using only one parameterization schemes, because sir already mentioned, Rakesh sir mentioned about the errors we are facing, like random error, model error, so those kind of error. But while we using only single parameterization schemes, we are not taking care of the model error. So using hybrid single, we have done the simulations, and then we have used hybrid multi, means to feed the model with, the data assimilation module with the model error also. That means we have used 30 ensemble members with different parameterization scheme combination. That is the hybrid multi. Because thunderstorm prediction, we face lots of issue, because only with hybrid it is not performing well. You have also seen in the radar data assimilation thing. So we thought like this multi-physics scheme may perform. And yes, it is somehow it is better than your hybrid single. If you see the pattern of this is 3D var, this is hybrid single, and this is hybrid multi. The intensity and the position, we cannot say accurate much, because we need to do lots of R&D, but there is differences in both the predictions. And 2 events we have also compared with the AWS stations. We have seen that hybrid multi with multiple parameterization schemes with model error we fuse into the model, your improvement is better. This red line, okay, this red line is showing the multi-physics schemes hybrid, and this is improving towards the end of the forecast. However, what about the initial time? For thunderstorm prediction, we are very much dependent on the initial hour, 1 to 6 hours, because thunderstorms are not a very long duration event. It just happen and dissipate. Because it's a synoptic event, means it retain for the whole day the rainfall, not the thunderstorm but the rainfall. That's why we get some indication of the heavy rainfall. But the initial hour of the thunderstorm we missed. And that is the problem that we are facing, because for that we need observations. Again, I'm advocating the same. We don't have observations, and that is why the initial condition what we are having to make the model understand, like some instability is there, convection is there, how we will feed the information using the observations. We don't have, we are dependent on global data or satellite data. So that is why the initial our informations are missed again here, and then maybe radar data assimilation may improve, or AWS network. And this is the comparison between WRF ETKF and EAKF. If you see the prediction with ETKF and EAKF, with EAKF, the location and location shift is there, but intensity is somewhat matching with the observed. That means the performance are comparable with observed and predicted with with EAKF. But still we need to do lots of, we have done around 15 case studies, and we have observed that intensity was captured well with EAKF, but still it has spatial deformation issue, like shifting in the spatial representation. So these are some of the research that we are doing for thunderstorm nowcasting, and operationally we are providing 3 maps daily, 3 hours lead time, and we run the thunderstorm nowcasting for March 15 to June 15. We use WRM model data, then from INSET 3D sounder data. We have developed an empirical method. So based on that method, we prepared a thunderstorm potential map, and those informations are sent via mail or SMS to the concerned state disaster management agencies. And we compare our observation, whatever thunderstorm potential map we prepare, we compare with in situ measurements like radar data that is available, that is there in Cherrapunji. And We also do lightning nowcasting, because lightning is another major problem, not only in northeast, like eastern India. Because of lightning, many people died every year. So we did some effort, like on R&D basis. We use the WRF ELAC model, and the lightning data that we receive from IITM, NRSC, we feed the data into the model, and this is the domain, this is the third domain. And now currently it is at 3 kilometer, but we are planning to 1 kilometer, because your lightning data density is very high. So if we go for 1 kilometer, then the model can consume more data, more informations, because you have dense observation, but because of the model resolution, you are losing information, and we are losing information. So we are planning to go for 1 kilometer resolution. Then data assimilation, we are doing lightning data basically, and the global data available. Then for validation, IITM and AWS data and DWR data we are using. This is just some predictions are showing here, like the probable lightning location that we got from the WRF ELAC model. And this is the observed. And if you see, it is well picked with some underestimation in the east, western part of Assam. And then this patch, if you see here also, it can identify. But the model accuracy is up to 4 hours, kind of nowcasting. With the time passes, the model accuracy also goes down. So that's why means we are, with this, we every 1 hourly we run the model, we give the prediction thrice daily for this also, because it is computationally very, very expensive. Because if there is a very dense lightning event there, then model will take almost 4 hours to run at 3 kilometer resolution, where for rainfall it will run only within 20 minutes. But depending on the density of the lightning data, the computational power need of the computational power also increases. That's why in collaboration with IITM and NRSC, we are setting up some lightning network all over northeastern region, and these data are only fed into the model. Earlier we are getting ENTLN data, but currently we are using only IITM data. And as we have seen, our forecast is valid only up to 4 hours. So we cannot depend for longer forecast on the model. So what we have done, we have also developed some empirical method using the lightning data from IITM. Then the core of some convective event identified using some algorithm has been developed, empirical and method has been developed, where the lightning data are used, and these polygons are showing, like this cursor, if you can see, showing how the system is moving to the next 45 minutes, and every 5 minutes this database get updated. So next 45 minutes, how the systems are moving to block level, this information can be given, but here we are not using any model. And as I have already said, this is a 45 minutes lead time, and block level alerts are given. And we also generate everyday daily lightning report also. If you go to the NERDRR website, in the report section, you will see any day you pick up, you will get a report like this. Like this is a 24-hour, 31st March it is written, so 00 UTC to 00 UTC 31st March. Accumulated lightning means it will be benefit if you want to validate also, spatial validation, visualization also. These reports are very handy. So we generate such report, and in our NERDR portal, these reports are readily available. If anyone wants to do some R&D over the northeastern region, some data related thing, means some comparison they want to do. So these reports are very useful. And then finally, whatever data we generate, it should go to the public. In the beginning only, I have said, like, the aim of NERDR is to give a common platform, a single window, whatever alerts we generate, how we disseminate this information. And we are not working in silos, like we work with IMD, CWC, IITM, then FSI for forest related thing, forest fire related. So all the alerts that NESAC also generate, all these alerts come to a common platform. The dashboard and one app has been developed for Assam State Disaster Management Agency. This is not freely available. This is developed for Assam State Disaster Management Authority. And then any alert comes to their dashboard, it's popped out also in the mobile. So any user, where if flood is happening or any lightning in the next 45 minutes is happening, so those alerts will be popped up if the person has installed this mobile app. So that way we are trying to help the, public also, because if we just do science, our organization is mostly application. So R&D component we are like trying to do. That's why I have done my PhD also. I traveled to IIST. I left my 3 years daughter for 6 months, and she's just started going to school, but for my schooling I come to IIST. And I'm lucky enough, like I get the opportunity to study under Chandrasekar sir, Govindan sir, and got so much of exposure, because being in the northeastern region, it's not only data sparse region, it's resource person sparse region also. So you will not get much more information. It means you don't, for example, like Amit sir was just mentioning during the tea time, he's lucky enough, he has got very good team, they're sitting behind. But we are not that lucky enough. We are very less people, like 40 scientists, permanent scientists, and in our team only 4 persons, and all are doing different things like lightning, someone climatology. So it's very difficult to make everyone work in a single thing. So research is a kind of bottleneck for us, but still we are doing it, because model accuracy will only improve if we update ourselves and update the model. And these are some of the publications. And this is our small team. This is headed by me, and under me, we have scientists, research scientists, and overall it is taken care of by head of Space and Atmospheric Science Division. And this is the thing that I want to share with you all. Thank you. And if you have any questions, I am ready to answer. Thank you.
Just one small clarification. This hybrid thing, you have yet to do it in the operational framework, right?
Yes, sir. Because the problem is, I already computational thing, but now we have got a World Bank project. Under that, we are getting one HPC. Amit sir also a committee member. So if we get that, then definitely, because everything is set up, and we have do the validation for our region, we are getting good results, but only the implementation based on the computational facility as well.
Okay, if there are no more questions, let us thank Dr. Rekha Gogoi for an excellent presentation.
Thank you so much. Now you may not be having any problem, but in future, if you do some R&D, if you face any issue, please approach me, no problem, because I have learned from people like Prashant. Prashant, he is my mentor, you can say. My WRF, I learned from him, sir. He is the person, and he is kind of willingly giving, this script you take, that script you take, because in scientific community also, you will not see this kind of sharing. People don't share. Mera code hai, main karunga. Kind of. It's not like that. With Prashant and team, it's really different. Paul sir, Prashant, and I'm very happy that I got the opportunity to be here among you. That is because of Kutty sir, Govindan sir, and Chandrasekar sir. Thank you. Thank you all.
So we are at the end of this 2-week data assimilation workshop. So I thank all the resource people, those who were involved with the lectures in the first week as well as in the second week. And I thank all the participants for sitting through all these lectures. I'm sure at the end of the 2 weeks you have all learned, and you all really possibly will take up something positive from this conference and use it in your research, and then take your research forward. We also have to thank ICTS, because it has been a very wonderful arrangement. All of you would agree with me that the arrangements in terms of accommodation, food, and everything has been really top class. And so I'm told that they will all send you emails to the participants, and they will want your feedback. So they give you about 15-day time, and then they will analyze the feedback and share it with us. Okay, so okay, thanks, and we'll just join for lunch.